We'll be looking at EDGECAM's automatic lead moves in this tech tip. We'll begin with a turning center with live tooling, and apart from our EDGECAM fundamentals training course. There are some flats on the part that have been machined with a live tool. Notice there's a perpendicular move as part of the leads, but when we open the profiling cycle and look at the lead page, the lead type is set to none. This is an automatic move that EDGECAM generates, and we'll be learning how to control this. Let's switch over to a milling application, also from our fundamentals training course. This is a simple panel that's milled in a 3-axis machining center. Focusing in on the finishing tool path, we can see that there are lead moves applied to the tool path, as is normal. On the outside of the part, we have a tool path that mills the edge of the part, and again an auto lead, while no leads have been requested. Now, the intent in this tool path is to mill the finished edge, the left edge in this case of the part, and when we look at the start-end page, we can see that the tool path intent is to start off the part, and we're using a formula or equation that helps EDGECAM build an intelligent relationship to the tool. We can see that on the general page, we're doing climb milling, and we have requested cutter compensation at the center of the tool. Now, if we turn cutter compensation off, notice that now the auto lead disappears. So undoing that, the auto lead is a function of cutter compensation being active. Now, if we go back into the cycle to point out cutter compensation, right, and then head to the lead page, let's ask for a horizontal lead type, equal lead moves. We'll use an angle of 45 degrees. And a lead radius of 1/4 inch. With these values in place, EDGECAM does build the lead we requested, and again, a perpendicular move. Let's generate code and look at what the NC code looks like. We'll code just the single cutter. Then when we look at the tool path, we can see that the cutter comp is activated on a linear move, and then the lead-in move happens. Now, this adheres to the rules in many machine tools where cutter comp activation and cancellation should not happen on an arc move. And that, in essence, is the reason for the automatic lead moves. If we go back to EDGECAM, edit the tool path, and modify the lead move so that now we remove the radius request, and instead just ask for a perpendicular move of 1/4 inch, notice that there's a perpendicular move with no further perpendicular run-on from there. So what we see happening is that the auto lead moves are built with consideration of cutter comp rules. We need to open the post processor to see what establishes the length of the auto lead move. So opening Code Wizard and an example post processor, we'll head to the machines section. Every EDGECAM post, whether mill or lathe with live tooling, has an input field for radius compensation factor. This post has a value of 1.5, and this is a multiplication factor that's used to determine the length of the auto lead. The equation EDGECAM will use is that whenever we need to calculate an auto lead, it is the tool radius, or half your cutter, multiplied against the radius compensation factor value. This calculation ensures that auto lead moves that run onto a part to establish cutter comp are always slightly bigger than the cutter, and that will generally avoid any cutter comp alarms when running tool path generated by EDGECAM in the CNC machine. Let's pause for a moment to review some cutter compensation information. The screen image shown is an example of a tool offset page in a CNC machine. For each offset register, there's a geometry value and a wear offset value. When the CNC machine is given a G41 or G42 instruction to execute, The coordinate sets that follow are adjusted by the combination of both geometry and wear. Whether the machine is given a G41 or G42 instruction depends on whether the EDGECAM cycle was designated as climb or conventional cutting. And then in the EDGECAM cycles, we can choose from none, centerline, or geometry compensation. Under none, the NC code is at the center of the cutter, and the machine operates under G40 and simply follows the given path, with no compensation done. When centerline is selected in the EDGECAM mill cycle, G41 or 42 will be output to NC code, and the NC code coordinates are at the center line of the cutter. The CNC machine should only be adjusting for the wear between the intended cutter size and the actual cutter size. When geometry is selected, G41 or 42 is output, but now NC code is at the edge of the cutter, so the CNC machine will be adjusting for both the geometry and wear offset values. Let's look at the cutter compensation controls typically found in EDGECAM milling cycles. When compensation is set to none, the generic graphic does not have a blue arrow and simply shows the NC code will be at the center of the cutter where the red lines are shown. When compensation is set to centerline, all of a sudden a blue arrow appears. Now we're going to be outputting G41 or 42 based on climber conventional, and the blue arrow indicates where the NC code coordinates will be, at the center line of the tool. When we change to geometry, there's still a blue arrow because of cutter compensation, but now it's shifted to the edge of the cutter. So we have graphical reminders about cutter compensation when active. These controls are available in many EDGECAM mill cycles, including popular ones such as the thread mill cycle, the chamfering cycle, and the hull cycle in the helical tab. Speaking of helical, let's build in some toolpath with this end mill to take care of the spot faces. So we'll insert before the move to tool change to insert it retroactively. And when I open the hull cycle, I'm going to go to my list of personal masks. And I've created a mask for different usages that I use the hull cycle for pretty regularly. When I choose the helical option, the dialog is instantly set up with the inputs that I feel are important for helical work. I don't have to go through the dialog box and set them all. So I can pretty quickly deploy toolpath by going and selecting first the target to machine. We'll select the hull features. Now notice that that picks all 4 hull features. And if I shade the features and render them in, you can see that these features include a counterbore. While there are other ways to build toolpath, the helical hull cycle provides ability to set depth that's relational to the preparation or counterbore depth, and then simply to assign my helical input parameters, which include cutter compensation. Now, if you don't have cutter compensation active in your helical cycle and it's grayed out, check the Control tab and turn on longhand. When it's off, which is typical for a brand new mill cycle, notice compensation is grayed out. So once it's enabled, cutter compensation is active, and we've quickly built helical mill toolpath and inserted it retroactively. We can see the toolpath. We see the auto lead that's generated. Let's go look at the NC code. Again, just for this tool. When we reload the code file and then search for helical that I put into the comment field in the cycle, we can see where that toolpath begins. And notice that the lead-in move is done on a linear move, as is required. The helical move, flattening off the counterbore at the bottom, turning off cutter comp, repositioning for the next hole, and repeating that process. So in summary, when we're in an EDGECAM milling cycle and we wish to use cutter compensation, we can do that without worrying about whether we'll have errors in the NC code because of cutter compensation rules. If we want lead-in moves, we can also request them. Taking a look at the machining process, we see the probe coming in to set up the work coordinate system. As we move into finished machining, the finished machining is done flawlessly, including things like the helical motion. We are confident that cutter compensation will output at the required time, turn off at the required time, and we'll be able to run our CNC machine with ability to run either under centerline or geometry compensation, whichever our company prefers to use. After machining is complete, the probe will be brought back a final time to measure key part geometries. Do you have questions on this or other topics? Please contact us to discuss. We would love to hear from you.